therefore this would be the other transition state. See? Right? Okay, so you need to match them, and which state is rate determinant? Obviously, this is the highest energy demand and slowest, and therefore that is the rate determining state, and it's going from B to C. Is the rate determining state. How many transition state? Again, the number of hills tells you the number of transition state, X, Y, and Z. So it's 3. So these are fairly straightforward questions if you recognize the. Alright, next problem. This was actually, I put that by mistake because there is one part of this question that relates to chapter 6 where we didn't go yet. Okay. So the last part, that the hydrogenation, this is from chapter 6. Sorry, but this is, I won't ask you this question. But let me do that anyway, quickly. This one tells you that you get an alkene, that after hydrogenation gives you this. So skeleton will remain the same. It's just you need to introduce a double bond. So C7H14 can be, let's write the skeleton here. And then you can introduce the double bond either here or here. So those are the two alkenes that are possible. And what is important to recognize is that it's telling you it's not a primary alkane bromide. So you cannot have the bromine here. The bromine must be here or here. So let's see which one would be possible. We are here or here. Now, it's also telling you this is a single elimination product is formed. So the single elimination product rules out this one because this would give you one here, one bond here. This is the only one that can give you single elimination product. So this is the A. And therefore, the B is this one. That gives you the final product. All right, I want to ask you this question. So carbon-carbon double bonds do not freely rotate like carbon-carbon single bonds. Why? And the double bond is much stronger and thus more difficult to rotate. That's not true necessarily. Overlap of the sp2 orbital of the carbon-carbon sigma bond could be lost. Sigma bond could not be lost. The short bond length of double bond makes it more difficult to attack groups to pass each other. That is also not true. Overlap of the two p orbitals of the pi bond would be lost. That is the correct answer. Rank the following substrate in order of increasing boiling point, and the boiling points really depend primarily on hydrogen bonding followed by dipole-dipole interaction. So the alcohols are always highest, and therefore you can see that there are two alcohols here. These two have the highest boiling point, and in one case you have a primary alcohol. The other case you have a secondary alcohol. Now, each of them have 3 carbon. As we have seen before, more branching essentially makes it smaller surface area and lower boiling point. Therefore, this will be the highest. This is number 4. Followed by this one, this is 3. And between this ether, which has an oxygen, therefore there will be dipole-dipole. This must be 2. And this is only a hydrocarbon. This is 1. This is the lowest. So, the answer is increasing boiling point, lowest to highest would be A, C, D, D, 5. Which one of the following reacts with AQR at the fastest rate? And again, we can see that the main reason these 3 are secondary alcohol. This is the one that's, all four of them are secondary alcohol. This is the only one that's tertiary. So this is the one that will also react with acid. And the final question is, looking at these two, you can see that the real difference is in the double bond. So this double bond has two hydrogens are on the same side. So this is really a Z. And this one has the two hydrogens on the opposing side. So this is an E isomer. So they are really stereoisomers. Any question? So concentrate on the reactions, you need to understand them and make sure that you know which reagent does. Everybody will get more than 90.